For this lesson, we're going to go over some fundamentals of transmission lines. Transmission lines consist of two conductors separated by a dielectric or an insulator. They are normally parallel lines such as coaxial cables, as you can see in the picture below. And also the depiction on the right shows how you might actually see it on exam or some questions. You're going to see the distance, which is represented by D, and that's the distance of the cable from the source to the load. You see R sub O, which is the characteristic impedance, R1, which is our source resistance, R2, which is our load resistance. And we'll go over some more of that in the examples. Unlike the typical circuits with inductors and capacitors, transmission lines, inductance, and capacitance are considered distributed parameters. Think of that whole long cable, that whole long coaxial cable. It is, in a sense, a long inductor and a long capacitor going down a whole line. That's what it means by it's distributed down the whole line. So if you look at the illustration below, we have that same depiction you would see in a problem, but also to the right, we have an inductor and a capacitor, and it's representative of that whole distance of D. Now the characteristic impedance, R sub O, is our inductance over capacitance, square rooted, as well as you can find our permeability and our permittivity based off those values. This slide right here is considered our meat and potato slide, the velocity of propagation. Electrical waves have a travel time between the source and the load. This travel time is measured with velocity and length, as we talked about with D for distance or V for velocity. And your distance can also be represented as wavelength. Now the velocity of propagation is the speed at which the wave travels. Pretty simple. The wavelength or distance is the distance the wave travels in just one cycle. And this is measured usually in meters. Now the equations I have below we'll go over in a practice problem or two. Those are a lot of your meat and potato equations. It's based off velocity, time, frequency, and distance, which is in meters. And be aware that velocity is measured using the speed of light, which is 3 times 10 to the 8. And we'll go over that more later in the lessons. Also, it's not listed here, but we'll go over it in a practice problem or two. The velocity factor. Signals are not always transmitted at the speed of light, which is 3 times 10 to the 8. Sometimes there's a velocity factor, which means you multiply that factor times the speed of light. So sometimes you might have a factor of 0.5 or 50%, and you would multiply this times the speed of light. And again, we'll go over that more in a practice problem. The parameter to be aware of when designing and analyzing transmission circuits is the reflection coefficient. Be aware when you send a signal down a transmission line, it may not have a matched impedance and a matched on both sides, load and source side. So it can create some reflection in your transmission line. So when a wave arrives initially, it's referred to the incident wave. When that wave or new wave is created, it is referred to a reflective wave or reflection. And the parameter that correlates to those is the reflection coefficient. And it's calculated or measured using the load resistance, the characteristic impedance, and source resistance, which we have in the two equations below. And we'll go over that in a practice problem. So when designing your transmission circuit, it's best to try to match your impedances up to get an ideal circuit. For example, if your source resistance matches your characteristic impedance, your source reflection is going to be 0. That is considered a matched generator. When your load resistance matches your characteristic impedance, that means your load reflection is going to be a matched load. Now, if both of those are 0, your load and your source reflection, it's going to give you a matched line. That is the best possible situation you can have. That's when your impedance on all ends is a match, which is great because that means the line will be fully charged at the end of one single trip, a one-way trip. And that is the ideal situation. However, it's very unlikely to obtain that matched line, but that is something you shoot for when designing. Since transmission lines have reflection, there's going to be some different states as far as the voltage and current of those transmission lines. Similar to RC and RL circuits, since a transmission line has an inductor and capacitor in a sense, there's going to be an initial state and then a steady state based on the timing. So there's going to be two models. The line model, which is our initial conditions, and then our steady state DC model, which is of course our steady state model after it's been on for a period of time. And below those two models are the two equations we'll use to find our final voltage and final current and their initial voltage and initial current. Okay, So you're thinking, all right, like transient analysis, is there a way to determine what the current or voltage is based on the time? Yeah, but we're going to use a bounce diagram to find this. The bounce diagram is a graphical depiction of how the reflection coefficient affects the current and the voltage. If you look at the illustration below, we have a first forward wave and a first reverse wave, and it's showing the signal being bounced back and forth until it's in its steady state condition. So by using this bounce diagram, you can determine what the voltage is based on where it's at in the timing of the circuit. Now, we're not going to go over the bounce diagram and how to calculate for this particular lesson just because of time and the details required. However, it will be done in a later video. For now, let's go ahead and do some practice problems to get our feet wet with the previous slides. Start off with an easy problem. For this one, we have a simple transmission circuit, and it says, determine the one-way delay time for the transmission circuit, assume the velocity factor is 1. So we're assuming for this one the velocity factor is 1, meaning that you multiply the speed of light times 1, which means the signal is transferring at the speed of light in a sense. So we want to assume the time delay. So we want to know how much is time. We're looking for t. All right. Well, let's see what we have. We have our voltage, we have resistance, we have the characteristic impedance, and we have the distance. Well, for this one, all we're going to need is the distance, just to determine time. And to our right, we have our equations. Time equals 1 over frequency, and equals the wavelength over the velocity. And I think that's the one we're going to use. So we're looking for t equals wavelength over velocity, or in this case, distance over velocity. Well, we know the distance is 5,000 meters, and we know the velocity is 3 times 10 to the 8 meters per second times 1, because our velocity factor is 1. Always remember that anytime there's a velocity factor, you got to multiply the speed of light times that factor. So we can plug and chug this one in our calculator, giving us an answer of 1.666, repeating, times 10 to negative 5. Or in our case, we can keep an engineer notation, 16.67 microseconds. So that is the one-way time delay for this transmission circuit. Yes, I did give you extra variables in here. I gave you the voltage, some resistance, and whatnot. Be aware that's sometimes given to you. You might actually have too much information. So we're just starting off with a really easy one just to get our feet wet. All right, let's go into another problem. All right, for this problem, we have a transmission circuit with a voltage source, a source resistance, and a load resistance, as well as our characteristic impedance. And we need to find the reflection coefficients, the line model, and the steady state model. And to the right, same as usual, I provide a few equations we can work with. So, start with number 1. We want to determine the reflection coefficients. Well, to the right, I have both our reflection coefficients. We have it on the load side and the source side. Well, this is mostly simple plug and chugging answers, but I figured we'd do it to get our feet wet. So, for the first one, let's go ahead and do our load side, which is going to come out to be R2, which is 200 ohms, minus the characteristic impedance, 150 ohms, over, and this is R2 plus characteristic impedance, so it's 200 plus 150, and we can plug and chug in that one in our calculator, giving us an answer of 0.143. Okay, same thing again, plug and chugging. I'm just doing a plug and chug one just to give you an idea of how simple it is, as well as what to look for and what not to look for. These are just simplified models. So this one we're going to have R1, which is 100 ohms, minus characteristic impedance, 150, over 100 plus 150, if my handwriting looks any better. And plug and chugging that one in our calculator is going to give us a reflection coefficient of negative 0.2. Okay? So the number 1, these are our two answers right here. For number 2, determine our line model. Well, our line model is our initial conditions, our voltage at initial conditions, as well as our current. And this is going to be a plug and chugging example. So for number 2, we're looking for VI, or V initial, and this is just our line model. This right here is our line model. This one's going to be our steady state model. Okay? So V sub I equals RO over characteristic impedance plus R1, which is 100, times voltage, which is 480 volts. This is going to equal, plug and chug in our calculator as usual, 288 volts. So initially, it's going to be 288 volts. And same thing with the current. We're going to plug and chug this one as well. Just get you familiar with these equations and know they exist. 480 volts, and then characteristic impedance, 150, plus our source resistance, which is 100. Again, plug and chug this in our calculator, 1.92 amps. So this is going to be our answer for the line model. All right, number 3, we're going to determine the steady state model. Very simple, plug and chug in as well. So this one we have R2, which is 200 ohms. This is our load resistance. Then plus R2 and R1, so that's 100 plus 200 times 480 volts. Gives us an answer of 320 volts. Now current is going to be also 480 volts over R1 plus R2, which is 100 plus 200. Plug and chug in that calculator as well. Gives us an answer as 1.6 amps. So this is going to be our final current. This is our initial current. Final voltage, initial voltage. And these are different. Is think of these as the transient analysis circuits we're doing, the RL and RC circuits. Since the transmission line acts as an inductor and a capacitor, you're going to have somewhat of a transient analysis here, hence the reflective coefficients. So just be aware of that. So it's nothing difficult. This is just to get our feet wet to the harder problems. All right, so let's go on to another problem. For this example, this is going to be more relevant to what you're used to seeing. Now we can actually move into a few more difficult problems and more realistic problems. All right, so we have a commercial AM broadcast station uses an antenna that is the wavelength divided by 4 tall. Okay? The height of the antenna with a station of a frequency of 800 kilohertz. All right, so we're looking for the height for this particular problem. So in a sense, you're looking for the wavelength. That's what we're looking for. Okay, what we know is the frequency equals 800 kilohertz, and we know obviously the speed of light, or velocity, is going to be 3 times 10 to the 8 meters per second. So this one's very simple. Look to the equations to the right. We have velocity divided by frequency. Very simple problem. So plug and chug in that one. Wavelength equals velocity, which is speed of light. Speed of light is something you're going to use very often in transmission line calculations, so it's best to get accustomed when using it. And over a frequency of 800 kilohertz. And then we're going to throw a wrench at you in a second. So we're going to plug and chug this in our calculator. 3 times 10 to the 8 divided by 800 kilohertz. It's going to give us an answer of 375 meters. All right, so right away you're thinking, oh, okay, that's the height of antenna, and that might be one of the answers. That's still wrong. Thing to be aware of is that right there. It is the wavelength divided by 4. So make sure you're aware of that when you read the problem. Yeah, you can find the wavelength, but divided by 4. So 375 meters divided by 4. That's pretty simple. Plug and chug in the calculator. Is 93.75 meters tall. So if you had an antenna, it only need to be approximately 100 meters. All right, let's do one more problem. All right, we got ourselves a good one right here. I saved the best for last. A RG6 coaxial cable has an impedance of 75 ohms and a velocity factor of 80%. In other words, 0.8. Determine the velocity, the impedance, the capacitance, and the relative permittivity. This one's going to be a fun one. This one has some realism to it. The 80% or 0.8 velocity factor is a real factor. RG6 is a very popular coaxial cable. So in a sense, we have a real-life application here. So let's tackle this one at a time. First thing we need to do is write what we know. We know R sub O equals 75 ohms. We know the velocity factor is 0.8. And I think that's all we know right now. So let's find the first item. Let's find the velocity. Like we talked about earlier, velocity is the velocity factor times the speed of light. So for this one, the actual velocity is going to be 3 times 10 to the 8 meters per second multiply times the velocity factor, which is 0.8. So it gives us a velocity of 40 times 10 to the 6. And that's going to be in meters per second. So that's relatively easy. As long as you memorize the speed of light, knocking transmission lines out is not too hard. Alright, so now we can find inductance, L. Well, look at my equations to the right. I have velocity, I have impedance, now I can find inductance. So since, I'll get to that in a second, since V equals RO over L, we could swap those two around, and it will give us L equals our impedance over velocity. Well, it's pretty simple. So it's going to be 75 ohms over our new velocity, which is 240 times 10 to the 6 meters per second. And we can plug and chug that one in our calculator, give us an answer of 3.125 times 10 to the negative 7. And this is going to be henries per meter. And let's make it somewhat engineering notation. Let's go ahead and say 312.5 nanohenries per meter. Next, we need to find capacitance. Alright, so we're looking for C. Well, same thing as earlier. I can use the equation down here, 1 over R sub O times C. So I can swap the velocity around with the capacitance. Pretty simple. Also, be aware of, I have my permittivity right there. Same answer. So right there, I can use either one of these equations to find our answer. It's just how you manipulate them. So this one's going to be 1 over our impedance times velocity. So that's pretty simple. So it's 1 over 75 ohms times 240 times 10 to the 6 meters per second. I'll try not to write that small. Let's see if we can clean that up. There we go. Alright, plug and chug that in our calculator. It's going to give an answer of 5.55 times 10 to the negative 11 farads per meter. And if I put that in engineering notations, we probably put that in pico. 55.55 picofarads. And the last one, relative permittivity. So we're looking for that guy right there. Well, looking to the right here, I have velocity, I have the speed of light, and then I have my permittivity right there. Unfortunately, it's on the wrong side. So for this one, we're going to have to swap those two around. We're going to have to swap these guys. So it's going to come out to be, that way you can see what I'm doing, as V equals speed of light over the square root of relative permittivity. Well, I'm going to swap those two around, so it comes out to be the square root of relative permittivity over speed of light over velocity. Well, I need to get rid of that square root, so I'm going to square both sides. So it's going to come out to be speed of light over velocity, and then that's square. And then I can plug and chug that in my calculator, 3 times 10 to the 8 over our velocity, which is 240 times 10 to the 6 meters per second for both of those. And we can plug and chug that real quick. We have 1.25, and then we have to square it. So square it in our calculator. It's going to give us an answer of 1.5625. And that right there will give us our relative permittivity. So that was actually pretty simple. Right there we did a realistic application where we found the velocity, the inductance, the capacitance, and relative permittivity just based off the characteristic impedance and the velocity factor. And this is a real impedance value and a real velocity factor for RG6. So we're able to find all these answers just based off those two variables. Later in other videos, we'll go over bounce diagrams and other ways to manipulate transmission lines.